All right, let's dive in. Today, we're tackling a really powerful idea from statistics called hypothesis testing. Now, don't let the name scare you. Think of it as a formal process for putting a claim on trial. It's a method for taking any claim, big or small, and really digging into the evidence to see if it actually holds up. So how do we do that? Well, let's step into the courtroom.
So, picture this. A huge company rolls out a brand new battery, and their ads are everywhere, claiming it lasts way longer than the old one. Do you just take their word for it? Probably not, right? You'd want to see some proof. Hypothesis testing is basically the rule book for that investigation. It gives us a structured step-by-step way to gather the evidence and make a fair decision.
And here's our game plan for this explainer. We're going to treat this whole thing like a courtroom drama. First, we'll put the claim on trial. Then we'll hear from the two opposing stories. We'll have to consider the risk of a wrong verdict, and because of that, we'll set a standard of proof. After that, we'll finally look at the evidence and issue a ruling. And lastly, we'll talk about why this whole process matters so much.
Okay, first things first. Every trial has to start by formally stating the claim we're actually investigating. And in statistics, this isn't some vague idea. It's a really precise statement that kicks the whole process off.
And that core claim, that central charge in our case, is called a hypothesis. It's basically an educated guess about some characteristic of a really big group, or what statisticians call a population. Everything that happens next is going to revolve around testing this one specific claim.
Now, you can't have a trial with just one side, right? You need a prosecution and a defense. And it's the exact same setup in hypothesis testing. We create two completely opposite stories, and our job is to figure out which one the evidence points to.
In one corner, we have the null hypothesis, which we call H0. Think of this as our defendant. It represents the status quo, the default belief. It's the nothing has changed, or there's no different story. And just like in a real court, it's assumed to be true until proven guilty. In the other corner, we have the alternative hypothesis, or H1. This is our prosecution. It's the new, bold idea that challenges the status quo. It's the hey, something is different here story. And, crucially, the entire burden of proof is on the prosecution to make its case.
But you know, just like in a real courtroom, things can go wrong. A jury can make a mistake. And in statistics, we don't just sweep this risk under the rug. Nope. We actually define it and we manage it very, very carefully.
So there are two big ways we can mess this up. The first is called a type 1 error. This happens if we reject the null hypothesis when it was actually true. In our courtroom analogy, this is a huge deal. It's convicting an innocent defendant. The other mistake is a type 2 error. This is the opposite. It's when we failed to reject the null hypothesis, even though it was false. This is like letting a guilty defendant walk free because we didn't have quite enough evidence to convict.
So if we have this risk of accidentally convicting an innocent defendant, we need to set a really high bar for the evidence, right? We need some kind of statistical version of proof beyond a reasonable doubt. So the question is, how much evidence is enough evidence?
But we have a name for that. It's called the level of significance, and it's represented by the Greek letter alpha. And here's the key part. We decide this before we even look at a single piece of evidence. It's our line in the sand. We're deciding up front on the absolute maximum risk we're willing to take of making that type 1 error of convicting the innocent.
In most scientific fields, the standard, the sort of default setting for alpha is 0.05 or 5%.
And what that 5% really means is that we are consciously and deliberately accepting a 1 in 20 chance that our conclusion might be wrong. Specifically, that we might say there is a difference when it was all just random chance. It's a calculated risk we agree to from the very beginning.
Okay, enough theory. We have the rules of our courtroom set up. Now let's see how this all plays out in an actual case. We're going to look at a claim about the average height of university students and walk through the trial, step by step.
And we're going to follow these 5 simple steps. We'll state the claim, collect our evidence, summarize that evidence into a single score, weigh it against our standard of proof, and then, finally, issue the verdict.
All right, here is our defendant, the null hypothesis. The established belief, the status quo, is that the average height for all male students at this particular university is 178.5 centimeters. This is the fact we're assuming to be true.
But wait, the prosecution brings in some new evidence. We went out and took a random sample of 225 students, and their average height came out to be 184.0 centimeters. That's a pretty noticeable difference from the old average, isn't it?
And that leads us to the absolute core question of this entire trial. Is that 5.5 centimeter difference real, compelling evidence that the old average is just wrong? Or could it just be a fluke? I mean, is it possible we just happen to pick a taller than average group of guys purely by random luck?
To figure that out, we boil all of our evidence down into a single number called a test statistic. You can think of it as an evidence score that measures just how surprising our result is. In this case, our evidence score is just 0.6875. Now, we compare that to our standard of proof. Remember that 5% significance level? Well, to get a guilty verdict, our evidence score needed to clear a bar of 1.96. As you can see, our score doesn't even come close.
And so, we deliver our ruling. Since our evidence score of 0.6875 is way less than the 1.96 standard required for a conviction, we fail to reject the null hypothesis. Now listen to that careful wording. We don't say the defendant is innocent. We don't claim the average height is 178.5 centimeters. We simply say that the prosecution didn't bring enough compelling evidence to convict. It's the statistical version of a not guilty verdict.
So you might be wondering, why go through all this trouble? Why all the formal steps and this super careful language? Well, because this structured, disciplined way of looking at claims is honestly one of the most powerful tools we have for making smart decisions based on data.
And this is not just some academic exercise. This exact process is used every single day in the real world. It's how we approve new medicines, how we test whether an engineering design is safe, how we know if a marketing campaign actually brought in more customers, and how we ensure quality in manufacturing. It's the best method we have for separating a real effect from just random noise. So, the next time you hear a big claim, whether it's in an ad for a new phone, a headline in the news, or in a business meeting, you now have the framework to put it on trial. It's a way of thinking that pushes you to demand real evidence before you believe something. So I'll just leave you with this thought. What claims in your life deserve a fair trial?